Okay, so for today, what I'm calling section 5.5, this is actually a really quick section. It's an idea called local linearity and how we can use this as an application of derivatives. So we've always defined differentiable as being the ability to find the derivative. In other words, that difference quotient where I can find the slope between 2 points that are moving infinitely close. And it's the same whether I'm moving the points from the left or from the right. So no corners, no cusps, no vertical tangents, no discontinuities. An alternative way to think about differentiability is that if I keep zooming in really, really close, the closer I get to the point of tangency, the point I'm zooming in on, the more and more my function starts to look like the tangent line at that point. This is what we call locally linear. It means as I zoom in closer and closer and closer, the function starts to look like it's linear very close to the point we're zooming in on. In other words, in that local area. That's why we call it locally linear. It's only in a very small frame that we're saying it's behaving like a line. But what that means is that if we are close to the point of tangency, because the function looks like the tangent line, or is really close to it, I can use the tangent line to approximate function values. And that's what we call the linearization of the function. Is we're saying, let's get our tangent line, isolate the y value in the tangent line, and that will be used to estimate function values. So an example of this, I want to find the linearization of j of x equals sine of x at pi over 4. Then use the linearization to estimate j of 0.8. And just kind of for your information, pi over 4 is about 0.785398. So 0.8 is close to that. So when I see that it says find the linearization, what that says to me is I need to find the tangent line and isolate the y. So to find a tangent line, it is a line. I tend to write equations of tangent lines in point-slope form, so I need to know a point and I need to know the slope. So the first thing I'm going to figure out is the point. They tell me that x is pi over 4. So to find the y, I need j of pi over 4. Well, that's the sine of pi over 4, which is rad 2 over 2. So this means my point is at pi over 4, rad 2 over 2. Then I need the slope. Well, slope of the tangent line is the same as derivative. So I need j prime of x. Derivative of sine is cosine. And then I need it at the x value I care about, which is at pi over 4. So j prime of pi over 4 is the cosine of pi over 4, which is rad 2 over 2. And then from all of this, I can write the equation of my tangent line. So y minus rad 2 over 2 is equal to my slope, rad 2 over 2, times x minus pi over 4. And then linearization does mean I need to isolate the y because what we're using this for is to estimate y. So I do need to get y by itself. So y is equal to rad 2 over 2 times parenthesis x minus pi over 4, close the parenthesis, and then plus rad 2 over 2. And here is my linearization. This is what I'm going to use to estimate function values that are close to the pi over 4. So they then say, well, estimate j of 0.8. Well, j of 0.8, I just take my linearization and I replace x with what I want, what the x is here, 0.8. So this is going to be approximately rad 2 over 2, parenthesis, my x is 0.8, minus pi over 4, close parentheses, plus rad 2 over 2. And then I am not required to simplify that, and that is my estimate.